All right, so this section we are looking at scatter diagrams and correlation. We are pretty much going to exclusively do it on our graphing calculators. So scatter diagrams, you started making those probably at least back in Algebra 1, if not before. Just when you had your XY grid, you put a dot for every point, and then you tried to find a line of best fit from that. You remember trying to draw a line about the same number of points above and below, writing the equation. Do you guys remember doing any of this? Yeah, hopefully. You have done it.
Definitely.
8th grade, yeah.
I don't remember that.
So we are going to have a more precise method. We're going to use a calculator to get the best possible line as we're going through. So it's really just a lot of learning how to use a calculator and some terminology things. So the response variable, we've talked about response and explanatory variables back in the first chapter, but just remember, the response is the variable whose value can be explained by the explanatory variable. So basically when we're graphing, your explanatory is like your x, your response variable is your y. So the response is the thing that's varying, that's our y value on our graph. The scatter diagram is just a picture that shows the relationship between those two things. So looking at those different points. So let's first talk about how to make a scatter diagram on the calculator, and then we'll start looking at some different things along with that. So this data is based on a study for drilling rock. Researchers want to determine the time it takes to dry drill a distance of 5 feet in rock. So if we look, the x is the depth at which we begin drilling, y is the time. When we set this up on our calculator, the x's need to go in L1, the y's need to go in L2. The second thing to remember, these are ordered pairs, so you have to put them in order. So if you miss an x value, is it okay to just throw it at the end on these? No, that will mess everything up, so you need to make sure they are in order. So now we are going to go into our stat plot. So second y equals. You may have multiple plots turned on, you may have none turned on, just depending on what your calculator is used for. If you have plot 2 turned on, go ahead and turn that off. We're not going to use that one right now. So I only want plot 1 turned on. And when I go into plot 1, turn it on, and the very first one is our scatter plot. You see a bunch of dots. So we'll select that, and it tells us your x is L1, your y is L2. Now if you just go to your graph, you're probably not going to see it, so we need to tell it where to look, so just hit zoom, and it's number 9, zoom stat. It'll take us to where our data is. So we should have a graph that looks like this. If it doesn't, then perhaps we must type a point. Is it not like it at all? Dang, Sam. Okay. Okay. Now scatter plot. You do. Alright. Anyone else having calculator problems? Okay. So could we get a scatter diagram on our calculator if we need to? All right. Now, looking at these scatter diagrams, we can see a lot of different relationships. These are linear. You know, if our data looks like a line, you can have increasing, you can have decreasing. In terms of lines, that would be like positive and negative slopes. Sometimes we have data that is not linear. But that doesn't mean there's no pattern to it. You know, if I look at this one, it's definitely not a line, but is there a pattern there?
Maybe like the weather or something.
Yeah.
Temperature.
So it's non-linear, but there is some kind of relationship. This is another situation where it's non-linear. This is one, it'd probably make more sense if there are a few more points here. But sometimes you just have like a random assortment of points and there may be no relationship. So we don't have to have a pattern. Sometimes we do, sometimes we don't. We are focusing on those linear relationships right now, but just know if it's not a linear relationship, that doesn't mean there's no relationship at all. All right, so back in algebra, you guys probably had to describe it as like a strong or a weak relationship. You know, is this a very good line or is this not so great? You remember this, I'm sure. We are going to be a little more precise. There is actually a calculation. It's called the correlation coefficient. This is a linear correlation coefficient. So it's only telling us how good of a model a line would be. So just so you know, if you look at your formula sheet, first bullet under chapter 4 tells us correlation coefficient is R, and it tells us how it's found. What does this symbol mean? Yeah, the sum. We're going to add them all up. This tells us our x minus the mean of x divided by what's s? Standard deviation of x. And then we do the same thing for y. Each y value minus the mean of y divided by standard deviation of y. We multiply those together, then add them all up and divide by n minus 1. It's a tedious calculation, okay? We are pretty much always going to do it on the calculator, except for we will try a couple by hand just with very small data sets. So there's a lot to this. If I do one by hand, I'm only going to give you a couple points, just to kind of make sure you understand what that formula means. So we'll look at one in a second. But things to remember, what that R is telling us. 1 is a good relationship. That means a line is a perfect match for that data. So if R is very close to positive 1, that's a perfect positive linear relationship. If it's very close to negative 1 is a perfect negative relationship. 0 is bad. 0 means the line is not a good fit. So the closer you are to positive or negative 1, the stronger the relationship. Positive increasing, negative decreasing. If it's close to 0, there is no linear relation. It doesn't mean there's no relationship at all, just that it's not linear. We don't have units on this, and the last thing, it is not resistant. Do you guys remember what resistant means?
Doesn't matter if there's a super huge number, it doesn't care.
If it's not resistant, that means if you have a really big or really small number, it is really going to throw off our R. Okay, so it is easily swayed by the outliers.
Cares a lot.
Well, you gave me what resistant meant. This one is not that. So this is just kind of showing what these might look like. In this case, it's a perfect linear relationship, so that would be when R is 1. Here, it's a pretty solid positive relationship, so that might be like an R.9. Here, is it still a positive relationship?
Yeah.
Yeah, but is it a very good one? No, so that one's about a 0.4. This would be a perfect -1, -0.9, -0.4. When I'm looking at these, this one just looks like a complete random assortment of points. That's R equals 0. This one is also 0, but is there a relationship here?
Yeah.
There's a pattern, but it is not linear, so that's why the R is 0. So an R of 0 doesn't tell us there's no relationship, just it's not a line. Alright, so let's practice doing one by hand, and then we'll talk about how to do it on the calculator. So if I wanted the linear correlation coefficient for this. Actually, can I do these out of order so we don't have to delete and then put data back into our calculator?
Yep.
Because I think, okay. I want to decide if example 1 has a linear relationship. Okay, so that data we just looked at, our scatter plot, remember, do you guys think that's a linear relationship?
Yeah.
looks fairly linear. Would it be positive or negative R?
Positive.
Positive. Okay, our calculators. We have to do something so that it will give us this value. So you are going to have to go in, and we need to go into the catalog. So second, 0. Now once this gets turned on a calculator, it will stay on unless the memory gets reset. So if you're using your own calculator, you shouldn't have to do the scan. If you're using one of mine, just anytime the data isn't popping up, you might have to go in here and turn it back on. We need to go all the way down to the D's. We want diagnostic on.
Oh, I remember this. It's the only part of this I remember.
So we hit enter. It'll tell us diagnostic on, hit enter, done. We're good. Now if we go into our stat calculus, this is all the stuff it can find. We want to see if a line is a good model. So we are actually going to have it write the equation of our line for us. Not because that's what I'm looking for right now, but that's the screen we go to. So number 4, linear regression, AX plus B. It tells me the A and the B, that would be like the linear equation, y equals mx plus b. But what I'm really concerned with is the R. If yours does not show you an R, that means your diagnostic is not on.
No, I remember.
Oh, you
Yes,
remember.
I remember.
So my R here is 0.772. Did everyone get that? What's wrong? Oh, it probably means one digit was off somewhere. Okay, so does this seem like it's a linear relationship?
Yep.
Yep, we feel pretty confident. Now the question is, what if it had been like 0.6? Would you think that was linear? Is that close enough
Yeah.
to be? What's the cutoff?
0.5.
0.5?
At half where it would round.
That-
Or 0.4, I guess, where it would round down.
Okay. There is an actual way to decide. So to test if it's a linear relationship or not, we look at the correlation coefficient, and then in your formula packet, there is a table 2. So if you flip through that a couple pages back, and try the back of the second piece of paper. So basically what happens is the bigger your data set, the smaller R can be and to still count as linear. And this is kind of a cutoff, the generally accepted norms. All right, so from my table, my critical value okay, our critical value is based on our number of points. So in that drilling data that we put in originally in here, how many points
12.
were there? 12? 12. Okay. So you would go to an n equals 12, and then the critical value associated with that is 0.576. That means anything bigger than 0.576 or smaller than negative 0.576 would be considered linear. So is our value linear?
Yeah.
Yes. So from table 2, that's a critical value. Since R is bigger than 0.576, the data is linear. Alright, sometimes we're just pretty confident, but if I needed a number to justify it, you compare it to that table.
It'd be great if
just greater than. Is that okay? So now let's talk about how to do them by hand. So I'm going to go back to this example. If I want to look at how that R is found by hand, I'm going to need some information. So the formula for my R, that's not bunch of random lines there. So our correlation R is the sum of x minus the mean of x divided by standard deviation of x times the y minus the mean of y divided by standard deviation of y over n minus 1. So I have to have some information from here. I need to get the mean of x, the mean of y, standard deviation of x, standard deviation of y, if I'm going to do this. Let's go ahead and just use our calculator to get that. So we'll have to enter it all into our calculator. And if you do them both at the same time, you can do the two variable statistics. So now we would need to make a table. I had 5 points, so I'll need 5 rows here. And I'm just going to go ahead and set it up as calculate my x, calculate my y's, and then multiply them. So, my first x value was 1. So I'm just going to type this all in my calculator at once. So I'm going to do a parenthesis, 1 minus the mean of x is 4, close my parenthesis, divided by the standard deviation of x, 2.449. It would probably be better if we had more decimal places. Definitely don't do less than 3 fours for the standard. Okay, did everyone see where I got this number? So I'm just going to go through. If you hit second enter, it'll bring back the thing we just typed in, and then I can just change my 1 to my next x value, which was 3. So we get negative 0.408. Next x value is also 3. Back and change it to a 6. And then 7. So, I got those values for my x. Does everyone understand where I'm getting these? Our x value. The x and then if you hit second enter, you can bring it back and just change. Alright, so now we do the same thing for our y. So our first y value was 18 minus the mean for my y is 10 divided by 5.612. Once I have all those, what do we have to do?
Multiply each line.
Multiply on each row. So I'm just multiplying straight across here. Tedious. Lots of calculator. Does everyone understand where I got my 15 numbers up? So now to get the R. The formula says, what does that symbol mean? Add up those products. So I'm going to add my final column together. Divide by n minus 1. So how many ordered pairs do we have to start with?
6.
I think 5. So 5 minus 1 will be 4. And I get an R of negative 0.944, approximately. What does that tell me? It's linear. It's a pretty solid negative linear relationship.
Is there a paper points like I got 0.946? I don't really know.
If you had rounded something to fewer or less places. Let's check it with our calculator and see how good we work. So we already have this stuff entered into our L1 and L2. So go to your stat, calculate number 4. And if we go through here, what letter are we
R.
looking for? R. And that was negative 0.9456. Were we close?
Yeah.
Pretty close. How come we're off a little bit?
Rounding.
We rounded everything to 3 decimal places. If we had kept 4 or 5, would we have been closer? Absolutely. So we can do it by hand. It's good to try one by hand so we kind of understand how to read the formulas, but time-wise, it's really not efficient. We're going to use the calculator when we need these. Are there any questions there? Mm-hmm.
Why did you go down one by recording this here?
Because the formula.
Oh.
All right, so last couple things I want to look at. This one is just giving us a scenario. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Does this mean that a higher percentage of females with a bachelor's degree causes a higher percentage of births to unmarried mothers? No. Why?
They're just related. That those 2 points you just related, they don't cause each other to
Yes. I want you guys to be aware of that. In stats, like pretty much we're always trying to decide if there's a relationship, but can I prove that one thing caused the other? No. So what I've shown is there is a relationship. But we don't know that one causes the other. So it's okay to tell me things are related. It's not okay to say, oh, that correlation coefficient is really close to 1, so it has to have caused it. This is kind of leads into what are called lurking variables. Lurking variables are just things we didn't consider that might be related to both of them. So, for instance, ice cream sales and crime rates have a very high correlation. So, does that mean that eating ice cream makes people commit crimes? No. What could be a lurking variable? Something that's causing these to rise and fall at the same time.
rolling blackouts.
Okay. Rolling blackouts. What causes, when do you eat more ice cream? When it's summer, when it's hot, right? Do crime rates go up when it's hot? There is a trend there. So these things go up at the same time, but they're actually totally unrelated. Okay, this ice cream sales have nothing to do with the crime rates. It's the heat. So the lurking variable here might be the heat. Or if you have rolling blackouts, because the heat is so high, there's energy demand when you have a blackout, do crime rates go up? They do. So those things are related. All right. Okay, I need to move through these last two slides. Because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers want to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the bone mineral density for a sample of 15 women. So if I'm trying to decide if there's a relationship, what would I need to do? All right, we need R. So I definitely don't want to do this by hand, so let's put it all in our calculator, L1 and L2. Alright, and then once you have it entered, where do you go to get your correlation coefficient?
Stat calc.
Stat calc. What'd you get for your R?
Negative 0.8056.
So we run that linear regression, and we're looking at that R. If I wanted to know, does this seem like there's a negative relationship? Probably. Let's look on table 2. Okay, how many points did we have? 15. So when our n is 15, the critical value 0.514. Now the table just gives me the positives, but if I were looking at the negative, it's just like saying a negative 0.514. So would this be considered linear?
Mhm.
Yes. It's a negative linear relationship. Okay, and we decide as long as the absolute value of R is bigger than the critical value. So 0.8056 is bigger than 0.514, so it's linear. The negative is just telling me that it's decreasing.
So if it's not in between, then it's not linear.
Yes. So if I had had like negative 0.4, that would not have been enough to assume linear relationship. It wouldn't have been a strong enough correlation. All right. Is that one okay? So final slide of the day. Figure shows the scatter diagram of that data. So can we conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? We can say they're related. Can I say that one is causing the other? No. What could be some other lurking variables?
Osteoporosis.
Okay, if you have osteoporosis.
Prior condition.
Okay, prior health conditions. Maybe it's calcium intake. If you're drinking 7 sodas a day, is there a chance that you're not drinking milk?
Yeah.
Yeah. So did the soda actually cause the loss of bone density, or was it the fact that there's no milk in your diet that caused the lack of bone density? So we can just, there's a lot of possible answers here, but you're just looking for some other possibilities that could have influenced these results. All right, so tomorrow is just a work day. If you're not here, then you are responsible for the homework. There's several that ask you to draw a scatter diagram. You're welcome to do it by hand if you really wanted to. I would probably just do it on the calculator. If I'm around, you can just show me and I'll initial your paper. If I'm not, just draw me like a really, really rough sketch of what it looks like. Okay? I'm not even asking you to put exact points, just enough that I can kind of see, yes, that is about the right trend for this data. Enough that I know you actually did look at it on your calculator.